My dear friends, welcome to Rajashekar classes on applied data science with Python. This is lecture number 569. In this lecture, we will try to understand SGD with momentum. Before understanding SGD with momentum, let us try to recap our SGD. So, in this section, we just quickly recap SGD and understand some of the limitations of SGD and introduce to a new concept called momentum and SGD with momentum. So, firstly, recap the SGD. So, imagine you have your weights WKIJ. What do we do in each iteration? What do we say? WKIJ nu equal to WKIJ old minus eta into derivative of loss function with respect to weights, isn't it? You are computing the WKIJ. Remember, you are computing the derivative of L. Derivative of L. Whenever you are computing derivative of a function, initially, let's assume you have W naught. Let me say W naught is my first approximation, then W1. Eventually, you will converge to W star, isn't it? Which is W star. What is this W star? Which is the minimum. When you start, you take random initialization where we compute the derivative. We compute the derivative at previous point, isn't it? Where will you compute? While calculating for WKIJ new, we will compute dou L by dou WKIJ at WKIJ old. But it means, what does it mean? The derivative you compute the derivative at previous point. You compute the derivative at old point. Previous point in the sense, I can say we compute the derivative at old point, isn't it? Because this derivative is tangent, isn't it? What is this derivative? Basically, derivative means what? Tangent. That's what we discussed in our previous lecture. Just try to remember what is the meaning of derivative. Is tangent. This is your what is this? This is your standard update equation. WKIJ new equal to WKIJ old minus eta into dou L by dou WKIJ. This is a standard update equation. Here, what I will do, instead of having ijk, every time, I simply remove ijk just for simplicity to understand, simplicity to understand. Whenever I write W, what I mean is, that is WK in the place of WKIJ, I will write W. That's what it says. Just see here, what am I doing? I am removing ijk, all these things. Just say I am removing ijk. Instead of ijk, just I am writing W. That's what it says. In the place of WKIJ, we would like to write it as W. I write W. What I mean is, and instead of saying new and old, here we are saying new old, isn't it? Let's assume you have iterations. Instead of saying old and new, let me call it as iterations, isn't it? Just see this one. Let me erase this first. Okay, yes, let's assume you have iterations. I will say iteration t and iteration t minus 1. What is WT? WT is iteration at iteration t. WT minus 1 is iteration t minus 1. Instead of new and old, you are saying at iteration t and iteration t minus 1. We start with zeroth iteration. You go to the iteration 1, iteration 2, up to the time you converges, isn't it? I simply rewrite this in much more easy to grasp notation. This is simple notation, so that we can easily grasp this one. I will say W at iteration t, WT means W at iteration t is equal to W at iteration t minus 1 minus eta into derivative of loss function with respect to W at iteration t minus 1. where do you compute the derivative? You compute the derivative at previous point, which is wt minus 1. What is this wt minus 1? It is at you are computing derivative at previous point. This formula is much more easy to read without ijk. It's much more simple to read. So we strict with this particular notation. Whenever I say t, it is iteration. It is at the tth iteration we use t, because with iteration time also increases. So let's start with this given this particular function, this particular relation. Let me say this is 1. Let me say this is 1. This given this formula 1 or relation 1 is simply update equation. So given this update equation, eta is typically taken as 0.0. This is simple update equation. Typically your eta value is 0.01. Eta is learning rate. Eta can change. Eta can change with iteration, isn't it? The hardest part to compute in this whole thing is your derivative. That's the most important thing to compute. So if you look at the derivative dou L by dou W, remember loss contains all the points, isn't it? Your loss contains all the points of your data set. It contains n points, d equal to xi comma yi equal to 1 to n. If you compute the derivative using all the n points in my data set capital D, we call it as gradient descent. Just try to recall gradient descent. If you compute it using only one point, let's call it as xi at random, xi which is randomly chosen from capital D, call it as stochastic gradient descent, isn't it? In the optimization chapter we discussed this in a lot of detailed manner. If you are not fully sure of it, please go back and revisit optimization lectures where we discussed this concept with a lot of details. The third option that we have is, instead of both these extremes, what are these extremes here? In first case, in the case of gradient descent, we are taking all endpoints, isn't it? And in the case of stochastic gradient descent, we are taking 1 point. Let's take instead of these two extreme cases, let's take a middle path using random subset of k points in D. Using random subset of k points in data set D. What is my D? D equal to xi comma yi, I equal to 1 to n. If it is the case, if you take random subset of k points, this is called mini batch SGD, isn't it? Why do we choose a limiting case, 1 point SGD, 1 point SGD, or I can say mini batch SGD? The reason is these are far more easy to compute. Imagine if you have millions of points in data set, if you use all points to compute the gradient, it will take a lot of time. We take k to be reasonable size, maybe 100 points, something like that, so that just computing gradient, if you take subset of points, computing gradient is little bit easier. In practice, in today's modern deep learning, these two are the most used. Which two are most used? SGD and mini batch SGD. To be truthful, this is what we most use. This is what we mostly used. Which one is mostly used? So we use mini batch SGD all the time. We don't use gradient descent. Gradient descent means taking all the points, isn't it? Yes. Now come to the problem. When you apply mini batch SGD, and let's assume I compute the derivative dou L by dou W with the help of mini batch SGD. Let me write this derivative of dou L by dou W computed using mini batch SGD. This is not exactly equal to gradient descent derivative, calculating derivative with respect to dou L by dou W with respect to gradient descent, isn't it? These are this one actually we would like to calculate dou L by dou W gradient descent. We want to compute it. As it takes lot of time, we are computing dou L by dou W with mini SGD. This mini batch SGD, this is, I can say, this is approximation. Dou L by dou W with respect to mini batch SGD is approximation of dou L by dou W with gradient descent. These are approximately equal. They are not exactly equal to each other, but they are approximately equal to each other. We are expecting to calculate gradient descent. Gradient descent computed. We are expected to calculate gradient descent, but computing gradient descent based derivative is very expensive. So we are using mini batch SGD as an approximation to the gradient descent based SGD. This is the most important thing about mini batch SGD. It is not perfect. This mini batch SGD is not perfect, but this is the most important thing about mini batch SGD. It is not perfect, but it is an approximation. Why we are calculating this approximation? It is difficult to calculate dou L by dou W with respect to gradient descent, as if your data set is very huge data set. If it has got millions and trillions of data points, calculating dou L by dou W with by using gradient descent is very difficult, in which case you have to consider all the points. So people are calculating dou L by dou W with by using mini batch SGD. I will continue my discussion in my next lecture, that is in 570. Just go through this lecture. Actually, what we did in this lecture, just we recalled the discussion what we learned in our previous lectures. In my next lecture, we will try to understand SGD with momentum. Thank you very much.